There is a plant that looks like a simple white daisy. For centuries, every farmer knew what it was. They grew it along their field borders, crushed its dried flowers into a fine powder, and dusted it across their crops. No chemical factory was required, no hazmat suits, no warning labels. The plant did the work of an entire pesticide industry, quietly, effectively, and safe. And then, almost overnight, it was abandoned. After 1950, when DDT conquered the world, this humble flower was pushed aside, dismissed as primitive, and nearly forgotten. But the flower never stopped working. We simply stopped paying attention. The plant is pyrethrum, specifically Chrysanthemum cinerariifolium, also known as the Dalmatian chrysanthemum. Despite what the title might suggest, it is not truly poisonous to humans. It is selectively lethal to insects while being among the safest insecticides ever known for mammals, birds, and human food systems. It is a perennial, daisy-like plant with white petals surrounding a bright yellow center, growing between 45 and 100 centimeters tall, with distinctive blue-green leaves. It is native to the Dalmatian coast of Croatia and Albania, and to the Caucasus region further east. Two main species exist. Tanacetum cinerariifolium, the Dalmatian chrysanthemum, is the more potent one. Chrysanthemum coccineum, the Persian chrysanthemum, carries the same compounds but in lower concentrations. The active insecticidal molecules are called pyrethrins, a group of 6 related compounds concentrated in the seed cases of the flower heads. These molecules attack the nervous systems of all insects by delaying the closure of voltage-gated sodium channels, triggering hyperexcitation, paralysis, and death. Even at sublethal doses, pyrethrins act as a powerful insect repellent, driving pests away before they ever touch the crop. This knowledge is not new. Pyrethrum has been used as an insecticide for centuries, possibly millennia. In the Middle East, it was known as Persian powder or Persian pellitory, and it was used to kill lice, fleas, and household insects long before anyone understood the chemistry behind it. Some historians believe it may have been exported from Persia to ancient Rome. By the 1800s, an Austrian industrialist named Johann Zackerl commercialized the substance under the brand name Zackerlin, selling it across the world. He held a United States patent from 1884 for pyrethrum soap. The substance was so widely known in the 19th century that Tolstoy referenced it in Anna Karenina. The character Kitty uses Persian powder to sanitize beds in an unclean hotel. This was not an obscure botanical curiosity. It was common household knowledge across entire continents. Before the age of synthetic pesticides, pyrethrum was the go-to insecticide. Every farmer who grew crops understood what this flower could do. In Japan in the 1880s, a man named Ueyama began cultivating pyrethrum flowers in Wakayama Prefecture and promoted their use across the country for lice control. His wife Yuki took the concept further. She invented the mosquito coil, a spiral of pyrethrum-infused material that could burn slowly through the night, releasing insecticidal smoke. That single invention became one of the most globally used insect control tools ever created, and it is still manufactured and sold today, more than a century later. The science followed the practice. Japanese biologist Fujitani published the first formal scientific study on pyrethrum's insecticidal properties in 1909. In 1923, the chemist Yamamoto identified the cyclopropane ring at the heart of the active compounds. Staudinger and Ruzicka fully described the chemical structures in 1924, and by 1944, Laforge and Barthel had confirmed the complete molecular architecture of pyrethrins 1 and 2. But farmers did not need to wait for the chemistry. They already knew what worked, and they did not just use pyrethrum as a spray or powder. They practiced companion planting, growing the flowers alongside their crops as a living pest management system. Pyrethrum produces a compound that mimics the alarm pheromone of aphids, the chemical signal aphids release when they are under attack. This repels aphids from the area. At the same time, the flowers attract ladybug beetles, which are natural predators of aphids. It was a dual-action, self-sustaining pest control system that required no spraying at all. The flowers simply grew, and the ecosystem did the rest. So what happened? In 1939, a Swiss chemist named Paul Hermann Müller discovered the insecticidal properties of dichlorodiphenyltrichloroethane, better known as DDT. He would go on to win the Nobel Prize in Physiology or Medicine in 1948 for that discovery. During World War II, pyrethrum supply lines were severed because Japan, one of the world's major producers, was an enemy nation. The Allied forces needed an alternative insecticide desperately. Malaria and typhus were killing soldiers in the Pacific Theater, and pyrethrum was no longer available in sufficient quantities. DDT filled the gap perfectly. It was cheap to synthesize from coal tar derivatives. It could be mass-produced in factories at industrial scale, and it was persistent in the environment, which at the time was considered an advantage. Spray once, and it kept killing for weeks. By October 1945, DDT was available for public sale in the United States. The government and the chemical industry promoted it aggressively, not just as a military tool, but as the future of agriculture itself. The numbers tell the story of what followed. From 1950 to 1980, more than 40,000 tons of DDT were used worldwide each year. Production peaked in 1963 at 82,000 tons annually. Pyrethrum, by contrast, was biodegradable. It had a half-life of roughly 12 hours in sunlight. It required growing actual flowers, harvesting them, drying them, processing them. It had to be reapplied more frequently than the synthetic alternative. In a post-war world intoxicated by chemical progress and industrial efficiency, pyrethrum looked primitive, quaint, old-fashioned. The entire pyrethrum-growing world felt the tremors as synthetic compounds flooded the market, and farmers who had grown these daisies for generations quietly stopped planting them. But here is what the post-war chemical revolution failed to account for. Pyrethrum is biodegradable precisely because that is what makes it safe. It breaks down in sunlight within hours. After 5 days, roughly 3% of the original compound remains. There is no persistent environmental contamination. It is considered among the safest insecticides for use around food crops because it degrades naturally or is destroyed by cooking. Its toxicity to mammals is remarkably low. The median lethal dose in rats, the dose required to kill half a test population, is approximately 1% of the animal's body weight, a threshold far less dangerous than organophosphates or organochlorides. Mammals metabolize pyrethrins quickly in the liver, and there is no evidence that the compounds accumulate or are stored in body tissues. The reason it devastates insects but spares mammals comes down to basic biology. Insects have higher nerve sensitivity to these compounds, dramatically smaller body mass, and lower body temperatures, all of which make them vastly more vulnerable. Unlike DDT, which bioaccumulates up the food chain, thins the eggshells of predatory birds, and persists for decades in soil, pyrethrum simply vanishes. It does its job and disappears. As a living plant grown alongside crops, it actively recruits beneficial insects while repelling harmful ones. It is, by nearly every ecological measure, superior. The catastrophe of DDT became undeniable in 1962 when marine biologist Rachel Carson published Silent Spring. Her research exposed the devastating downstream effects of persistent synthetic pesticides. Eggshell thinning was driving bald eagles, peregrine falcons, and brown pelicans toward extinction. DDT was bioaccumulating through entire food chains, concentrating in the fat of top predators, including humans. Cancer concerns mounted. Public outrage followed. DDT was banned for agricultural use in the United States in 1972, a full decade after Carson's warning. A worldwide ban on agricultural DDT was formalized under the Stockholm Convention on Persistent Organic Pollutants in 2004. By that point, an estimated 1.8 million tons of DDT had been produced globally since the 1940s, and persistent contamination remained measurable in soil, water, and animal fat across every continent on Earth. Meanwhile, the primitive flower that farmers had relied on for centuries had posed none of these problems, not one. Today, pyrethrum is experiencing a quiet renaissance. Kenya became the world's dominant producer, growing roughly 70% of the global supply since the 2000s. The plant was first introduced to Kenya's highlands in the late 1920s, and its cultivation became a critical economic activity for smallholder farmers. Tasmania in Australia has also emerged as a major production center. Pyrethrins are now gradually replacing the organophosphates and organochlorides that once replaced them, because those synthetic compounds have been shown to cause significant and persistent toxic effects. Potato leaf hoppers, beet leaf hoppers, grape leaf hoppers, cabbage loopers, stink bugs, cucumber beetles, thrips, and cranberry fruit worms are all successfully controlled with pyrethrin-based treatments. The irony is difficult to overstate. We abandoned a working solution, spent decades poisoning the planet with its replacement, and are now returning to the original answer. But honesty demands acknowledging what pyrethrum cannot do. It is highly toxic to fish and aquatic invertebrates, even at very low concentrations. Runoff into waterways is a genuine environmental concern. It is highly toxic to bees, with fatal doses as small as 0.02 micrograms, meaning it must be applied at night and in liquid form to minimize harm to pollinators. It can trigger allergic reactions in some people, including dermatitis, rhinitis, and asthma, particularly from the crude flower powder. Cats lack the liver enzymes to metabolize pyrethrins, making it toxic to cats. And its rapid degradation in ultraviolet light, the very property that makes it environmentally safe, means it must be reapplied more often than synthetic alternatives, a real cost consideration for large-scale commercial farming. It does not completely replace every pesticide in every context, no single solution does, but for many pest-crop combinations, it is remarkably effective and far less destructive than the chemicals that replaced it. It is also worth noting that the synthetic derivatives called pyrethroids, compounds like permethrin that are modeled on the natural pyrethrin molecule, have been engineered specifically for greater environmental persistence. In doing so, they reintroduce some of the very problems we spent decades trying to escape. The real story here is not just about a plant, it is about how an entire civilization discarded centuries of accumulated agricultural wisdom in a single generation. We traded a biodegradable, flower-derived insecticide for persistent synthetic poisons because the chemicals were cheaper to produce and the marketing was louder. We let industrial convenience override ecological common sense. Every farmer before 1950 knew this flower. They grew it, they used it, they trusted it. The question that should trouble us is not whether pyrethrum works. The science has confirmed what farmers always knew. The question is why we forgot. If you grow a garden, you can grow pyrethrum daisies along your borders today. The seeds are commercially available. The knowledge is accessible. The flowers still work exactly as they always have. The only thing that changed was us.